Log on, tune in, find out. Another good idea from Cambridge.
Yeah, the first talk this morning is the first talk of the series by Arun Ram on symmetries, polynomials, and quantisation.
Thank you.
Oh, and not to remind you to turn your mobile phones off because they've been interfering with the recording. So everybody's supposed to turn it off. And I guess that probably means actually off rather than like silent.
Okay, well, thank you. It's for me a great pleasure to be back here at the Newton Institute. In 2001, I was here for the McDonald Polynomial Program, and it was one of the best, for my whole family, it was one of the best times. So I'm very much looking forward to the next. Unfortunately, I can only say 6 weeks, but I'm very much looking forward to it. And in fact, so about a month ago, I thought, well, maybe I should start to prepare these lectures. And I looked at the title, Symmetry, Polynomials, and Quantization. I said, what the heck does that mean? And so in fact, I've been thinking a lot about McDonald polynomials the last year and a half or so. And so we'll go back to 8 years ago and talk about McDonald polynomials. So my plan for the talks is that essentially today, if you might call symmetry, and tomorrow you might call quantization, then on the third lecture would be something essentially flag varieties, geometry. I need to connect to geometry. And then the last lecture, we'll see how much time we have left, but I would like, if we have time, to talk about the Weil character formula for McDonald polynomials. This is a beautiful story. So that's my plan. Being symmetry, this is what I mean by symmetry. And somehow, if I could put a whole point to what I would like to get across, is that you must believe in this picture. This is really the heart of the way that I work with an algebraic group or with a compact Lie group, is always with this picture. And so that's more or less the only thing that's in my head. Okay, so let's start to build the story. The story, let's begin it with reflection group, which I will call W0. So a reflection, let's try to define a reflection, is some matrix, let's say in GLN. Let me put C, but as Von Jones says, C is an arbitrary field, right? So I don't really know what I want C to be, but we'll put C for now. With exactly one eigenvalue not equal to 1. All right, so I wanted this series, being an introductory series, I wanted to talk about fundamentals. I sort of had in mind to talk about fundamentals. And the more I prepared the lectures, the less I was confident that I understood the fundamentals. So in fact, I'm not sure that I like this definition of reflection. All right? Because in my head, this is not a reflection. In my head, for me, S is conjugate to, what I have in my head is conjugate to a matrix which looks like this. So it's all ones, and then it has one diagonal entry which is not one. Now, of course, these two are not quite equivalent, but in my head they're the same. And so I don't really know what. Sorry?
Do you want S to be a finite or not?
Well, in this example, S is a finite order. Whether I really want in the grand picture, whether I want S to be a finite order, I'm not sure. But for today, it will be a finite order. Yes. Okay, so the next piece of data is I need two lattices, which I'm going to call HZ and HZ star. So these are dual Z vector spaces. So as a vector space over the integers, is a free Z module. So you know what a vector space looks like. It looks like this thing, and then this is a Z vector space, a Z vector space. It's integer linear combinations, and they're paired for me by a pairing which is now. This is one of the unpleasant things in the theory. I would like to have everything. I would like to have C be the integers, but then if I try to do that everywhere, I run into little problems, and so sometimes I need to fix by dividing by a little number. So E, where E, just take E to be 1, but there are a few examples where E is 2 or 3 or something. So most of the time E is 1, but there's a pairing which pairs these two. And I think of, if I were thinking of that as a real vector space, then this is functions on that. And I really want to keep these separate. I don't want to identify them, even though there's this nice pairing which pairs them. OK, so W naught then is a finite subgroup of GLHZ. So that's a very interesting statement. It means that the matrices, first of all, W naught is matrices. It really is matrices. And these matrices have integer entries. I'm forcing some rigidity, very strong rigidity into this. And I want it to be generated by the set which I call R plus, which is all of those elements that it contains, all of those matrices which are reflections. All right, so for me, this is what I will call R plus. All right? R plus. In my head, it's something like positive roots, but it's the reflections in this group. So that's a very rigid structure. So what does it look like? In my head, it looks like this. It's there. Okay, so it's symmetries of that square. All right, now one of the things for reflection is that okay, so W naught acts on the dual space by, so W acting on a function mu evaluated at lambda check is mu W inverse lambda check. So W is W naught, mu in HZ star, lambda check in HZ. Okay, so I'm going to be quite careful. I'm trying to be quite careful about the difference between H and H star.
Where do the denominators go now?
Yeah, this is a good question. I just put denominators when I need them. So I don't know exactly. When I need to do a computation, I put the denominator, and then I look later. That's, I think, the right way to think for right now. Okay, so good. Now I need to fix two pieces of data for each reflection. I think you can see at the bottom of this. So let me try to put it. So if S is an element of R plus, then we fix alpha. So I'm confused about whether I should put the S here or not. It certainly depends on S. So this is going to be an HZ star and alpha S check, which is in HZ. So that I can write formulas for these reflections. S acting on mu is mu minus mu inner product with alpha S check, alpha S. And S inverse acting on lambda check is lambda check minus lambda check alpha S check. So the pair alpha S check is actually unique up to a constant. So there is a choice here, but I will fix them most of the time. And if you normally work with root systems, you require that to be all invariant under the actions of the W. Okay, so that's the data that we want to start with. Okay, so what I want to build now is a beautiful object, which is the double affine Weyl group. So the double affine Weyl group I will call W tilde. So this is Q to the K on E, X to the mu, W, Y to the lambda check. So K is in Z, mu is in H Z star, W is in W naught, and lambda check is in H. Okay. With the following relations. So Q to the 1 over E will be in the center of W tilde. So it commutes with everything. All right? Now the x's, they form a copy of the lattice. So HZ star is a lattice. It has an addition. I'm going to write exactly the same group but with multiplication. All right? So the x's are exactly the same group as HZ star, but written multiplicatively. And the y's are exactly the same group as HZ star, as HZ, but written multiplicatively. Okay? And then there's the rule for pushing x's past y's is Q to the mu evaluated at lambda check, Y to the lambda check, X to the mu. All right, so if you want to push x's past y's, you can do it, except that the form will come in here. And finally, it's a semi-direct product with W. So W x to the mu is x to the W mu W, and W y to the lambda check is y to the W lambda check. All right, that's the double affine Weyl group. It really is I'm more and more fascinated by this object. Okay, so before we can, so what I would like to produce is a braid group for this double affine Weyl group. But unfortunately, I do not know the right definition of this braid group. So I have to tell you the wrong one. I mean, it's correct, but it's not philosophically quite right. So in order to do this, I'm going to first put the focus on 1/2 of this double affine Weyl group. So the affine Weyl group, I will call it W check, is the piece which is x to the mu W. HZ star W in W naught. Okay, so this is just somehow the x half of the double affine Weyl group. Now this thing has a very nice action. So this acts, W check acts on HR star. HR star is just extend coefficients so that my lattice has disappeared and now it's just the plane. Okay, so I've just extended coefficients so that it's two-dimensional R real space. And I'm going to make this action so that, well, W already acts on mu. That's not a problem. I already have W. W0 is already acting on HZ star. So I just extend linearly. But I need x to the, let me write it this way, mu to act on nu. And this will be mu plus nu. So it acts by translation. Okay, now this action is very nice in the sense that it essentially has fundamental regions. So the alcoves are the connected components of, so I will take the real space and I will remove a bunch of hyperplanes, which I will call H alpha check plus KD, and I guess now if you're gonna worry about the denominators, it's gonna drive me crazy because it should be probably, I'm sure there should be denominators here. So now this is a very common thing to do is, you see, this alpha essentially determines S, because S is the reflection in the hyperplane orthogonal to alpha. All right? So whether I call it alpha or I call it S, it doesn't really matter. Now, if I really were working in a complex reflection group, so when I'm working with Z, then this C is plus or minus 1, because the determinant must be an integer. So that makes my life a little bit easier. But that's what I'm doing here. So instead of writing S, I'm writing alpha check, and I'm just labeling those reflections by these co-roots instead of by the reflections. Now, what is this object? This is a hyperplane. So H alpha check plus KT is all of those elements which are distance negative k from, I guess I have to put k on negative k on E from alpha. So that now we have, so this is the picture I put at the beginning. This is exactly this picture. All right, so we might call, so I don't know where the origin is anymore. Let's say that the origin is here. Then this hyperplane is something like H let's call this point epsilon 1 and this point epsilon 2, so that this is H epsilon 1 check and this is H epsilon 2 check. That might be a nice way. This is some H epsilon 1 check minus epsilon 2 check. And then this hyperplane here is H minus epsilon 1 check minus epsilon 2 check plus D. And this hyperplane here is H minus epsilon 1 check plus 1/2 D. All right, so if I shift a hyperplane, that's where the D appears. And the amount of D is telling me how much I shifted the hyperplane. So this minus epsilon 1 check is this blue hyperplane. Okay, and if you notice that blue hyperplane is half epsilon 1 away. So that's why the half. So somehow it's all designed in the rigidity of this thing. All this picture is designed. I've taken my real two-dimensional space and I remove all these hyperplanes, and what's left are all these little alcoves. So the alcoves are the triangles. I said you must believe in this picture. Okay, so this is thing. And if you think about the action of this affine Weyl group, well, when I translate by an element of the lattice, this fundamental, where did it go? My fundamental square. Here it is. Yes?
Is that D just a symbol or a number?
Just a symbol. It's just a symbol which tells me how much I shifted the hyperplane. It's D. For me, the definition of this hyperplane is that.
Should be a D there, KD, is that right?
No, that's a number. I take an inner product and I get a number, and that's a number. But this symbol, I include the D in there because I'm crazy. Because in the back of my head there's an affine Lie algebra with solutions and so on. Okay, but the D, if you like, means nothing. It's just a label to tell me how much I shifted it. Okay, so this, so if I take my fundamental square like this and I shift it by epsilon 1, if I shift the whole picture by epsilon 1, well, it's clear that alcoves go to alcoves. So it's acting like it's got fundamental regions. Okay, but great. All right, so that's my story. Now what I'm going to do is I'm going to fix an alcove C such that 0 is in the closure of C. All right, so in this picture, maybe we should just draw it again, because I'll need to point to it. Because I need to build this little by little. So here's this fundamental square of mine. This is the point 0. This is the origin in that picture. And I choose an alcove that contains 0 in its closure. So my favorite one to choose here is this one. Okay. 0 is in the closure of that alcove. All right. Okay, so there's another one of these triangles here. All right. Now, I'm going to put a bunch of labels according to this special choice of fundamental alcove. So H alpha 0 check up to H alpha 1 check, H alpha n check are the walls of this C. So here, let's see if we have some colors. So this is a wall, this hyperplane, which is H epsilon 1 check minus epsilon 2 check. And this hyperplane is a wall, which is H epsilon 2 check. All right? And finally, we have only two. Let's take this one. This is H negative epsilon 1 check plus 1/2 D in my example. So this is what I would call H alpha 0 check. This is H alpha 1 check, and this picture here, this wall is H alpha 2 check. Okay, so I'm going to fix these walls, and then I define S0 check up to Sn check are the reflections in these walls. Okay. And finally, there's a problem that we don't see it in my example, but we would see it if I did some more examples. And that is that chamber might have some stabilizer. So there are examples where there are some elements of the affine Weyl group which stabilize this chamber. So let me just give you an example of how it could happen. It doesn't happen in this one, but is if I took this chamber C and I reflected it over to here, and then I, reflect over to here, and then I translated it back. All right? If I have enough translations, then I can take this chamber and translate it back. That would be an element in this group omega check. Okay, so omega check is a small finite group, which is just some kind of symmetries of this thing. Okay, so that's the data I need to fix. I want to make one point here, and that is that this C is the extended affine Dinkin diagram. Okay, I don't use Dinkin diagrams because I have this C. This C is the dual. If you take the dual, what do you call it? Dual graph or dual. If you put a vertex on each of these faces and then connect them appropriately, you get the Dinkin diagram. So this C is a replacement for the Dinkin diagram for me. And so that's essentially what I'm doing. I could have talked about root systems and Dinkin diagrams, but I don't. I just believe in this picture. All right, so what we get here is the following story. So first of all, this W naught that we started with is now a pictorial object for me. This is alcoves in the zero octagon. All right, so there's the zero. This is the octagon that has center 0. And I'm going to label, this is S1, this is S2, the way I have it. This is S1. Can you see the purple? Yes? Okay. This is S2, S1. This is S1, S2. This is S2, S1, S2. S1, S2, S1. S1, S2, S1, S2, which happens to be equal to S2, S1, S2, S1. And those alcoves are W0. Okay? That's exactly W0. So when I say W0, what comes in my head is this picture of that purple thing at the origin. All right. All right. Now, HZ star is the set of octagons. Then. All right. So this, let's see if we can. This was my lattice, and hopefully you can see that that's exactly the same as the set of these green octagons. So the lattice can be identified with the green octagons in my picture. All right? So instead of talking about a point in the lattice, I often just talk about one of these green octagons. And then the whole affine vial group, W check, is in bijection with all the alcoves. So I would like to put here HR star, but that group means that there's some extra stabilizer which I must put into the game. All right? So I think of this as omega check sheets of HR star, and the G checks are deck transformations. So these G checks, I need to make the action, what do you call that when an action has a real fundamental, has only, that nothing has a stabilizer?
Simply transitive.
Simply transitive. I need to make the action simply transitive. If it happened that there was some stabilizer of C, I just fix it by creating a new copy of C, and I create as many copies as I need so that I have 1 sheet, 2 sheets, 3 sheets. And as long as I take 3 sheets of HR star, then the action is simply transitive, and I get a bijection between.
So I think I don't understand what that product means. I mean, it's well, or how W check acts on it, I guess.
So let's put it this way, that the G check, okay, let's write it straight. G check maps to G check cross C. Does that help? No? That doesn't help. So let me see if I can do it here. It's always better to do it on the picture. So here I have 1, which is
It's the omega check that I'm worried about.
yes.
I don't understand what geometric object you're attaching to W check when omega check is not trivial.
Okay. So this is HR star.
This is manifestly not an example.
But I'm going to make it into an example. So suppose I add the translation, which is from let's call this gamma, which just translates this picture so that gamma lands on 1. Okay. So if I add that translation in, then this chamber C has some stabilizer, because I could do S2, S2, S1. This is S2, S1, S2. And then I translate. And if I just act on this, that has some stabilizer. All right? So I want to fix that. So I create a new space with a new action. The new space has 2 sheets. All right? One which is down on the lower level, which looks exactly as before, except that this bad translation takes you from the bottom to the top sheet. It's a deck transformation that moves you up. Right? It's just a combinatorial trick for making the action simply transfer. So that's, if you want it topologically, it's just it has the discrete topology. Really separate these sheets so that there's no twisting between. Is that okay, David? You don't look happy. Okay. So the next thing that I need to say is that this affine Weil group has another presentation, which is actually, I thought of another way to draw it, but I want to go ahead so that I'll draw the other way in the discussion section. I thought of another way to draw the 2 sheets on this board. So ask me again in the discussion section, and I'll do some I'll do some computations to show you. Okay, now W check is presented by generators S0 check up to Sn check and omega check. So, I mean, now I'm abusing notation again. I really want this, I could generate a group by some subgroups. So I really want this omega check to be sitting there as a subgroup. I'm not going to rewrite the relations of omega check. So this, okay, with the following relations. So Si check, Sj check, Si, Sj, Si, Sj is Sj, Si, and so on. Mij check times, where pi over Mij check is the angle between the corresponding walls. So if I want this Mij check, I go look at those 2 walls. I look at their angle, and that angle is pi over 4. So I do S1, S2, S1, S2 equals S2, S1, S2, S1, pi over 4. Right. If I want the other one, if I put an S0 check here, and I want to know what's the relation between S2 check and S0 check, I look at the angle. It's pi over 2. So S0 check, S2 check is equal to S2 check, S0 check in this example. So that's what that relation says. I can read it I don't need a Dinkin diagram because the chamber has the information for me. And I'll have G check, SI check, G check inverse is S of GI check, where G check acting on a wall is H of alpha G check. Okay, so this G check takes the chamber to itself. Right? This G check and translates it back. It takes the chamber to itself, but it might have switched the walls in the process. All right, so this keeps track of any switching of walls that happened when you moved the chamber to itself. Right? For example, I can switch that purple and that red wall. That's an automorphism of this chamber. Sometimes that may occur. And finally, SI check squared is 1. Okay. So that's a completely different presentation of this affine Weyl group. Completely different than that one, which was x to the mu's and w. And I'm going to, unfortunately in this subject, we don't know how to do everything with only one presentation. So we flip back and forth between these two presentations all the time. All right. Let's, so now I can tell you what is, maybe that's, we'll keep that. What is the affine Bragg group? Okay, so the affine Bragg group, B check. So the affine Bragg group B check has generators. So generators. T0 check up to Tn check and omega check. I keep omega check as a subgroup, so I'm using it. I'm including the relations that are already in omega check with relations. So Ti check, Tj check, Mij check is Tj, Ti, Mij check. And G check, Ti check, G check inverse is T G of I check. So it's exactly the same, except I forget that last one. That last SI squared is not there. That's the affine Bragg group. Okay. Now, one of the things that I've done is I've put in checks everywhere. I've done this with the check one. I want to stress that there's another affine Weyl group inside the double affine Weyl group. There's an affine Weyl group that has y's instead of x's. And I could do the whole story with that affine Weyl group, and I get a non-checked one. So both the checks and the non-checks are inside the double affine Weyl group. And this is actually a very important statement, which is some shadow of Langland's duality. So we need these two versions of the affine. It's easier to take the checks off than to put the checks on. So I tried to help you by doing it with the checks on. So that's okay. So we've got an affine Bragg group. Now I can define the double affine Bragg group. Okay. So now my goal is to define double affine Bragg group. Okay, so I know what the single affine Bragg group is. And I'm going to need one piece of information here. So W check is this group that we've been working with. Now this group acts on another abelian group, which is q to the k on e, y to the lambda check, k and z, lambda check and h, z, by conjugation. Both of these are inside the double affine Weyl group. The double affine Weyl group contains both x's and y's. And so we can just take an element in here in W check, we can take a y and we can conjugate by that. All right? When you do that, it's back in y tilde. All right? So I'm going to note, so the notation is that I will call this y to the u lambda check. Lambda check in hz. But this is a tricky notation because that conjugation may contain a q. So this thing may contain a q. All right, so there are some q's in that, but I need this notation. All right, now we can define the double affine Bragg group. All right. Double affine Bragg group B tilde is generated by the group B check. So that affine Bragg group B check, it's got the T checks and those relations, and the group Y tilde. All right, so I'm saving myself some work by generating these by groups, not just sets, so that I don't have to rewrite all the relations over again. All right, all the relations from those previous groups are in the double affine Bragg group with some more relations. So Q to the 1 on E is in the center of the double affine Bragg group. G check Y to the lambda check G check inverse is y to the G check lambda check for G check in omega check. All right, that's I'm using this notation now. So I've played a trick. Here I define this notation by using that presentation inside the double affine Weyl group. I use the x's and the w's to define this notation. But of course, this W check has another presentation which contains the G checks. And I'm now using the other presentation of W check to write relations here. And TI check inverse y to the lambda check is y to the SI check lambda check, TI check inverse if lambda check alpha I is 0, and y to the SI check lambda check TI check if lambda check alpha I is 1. All right. So I used the TIs and the G checks to define this double affine Bragg group. If you figure out how to define this double affine Bragg group with only the x's and the y's with the other presentation, I would be very happy to know. How do you do that? At the moment, I don't know how to get these relations in terms of just the x's and the y's. It should be there, though. Okay, so that's the double affine Bragg group. It is certainly an important fundamental creature. It has everything to do with the geometry of the Langlands correspondence, I'm sure of it. Okay. So we're not always interested in the whole thing. We're interested in a quotient of it. So I'm going to try to build that quotient now. Affine Hecke algebra. And this is, so foreshadowing what we're going to do, the affine Hecke algebra comes from a p-adic group, or from an affine Kac-Moody group. And it's expected that this double affine Hecke algebra comes from a p-adic affine Kac-Moody group. All right?
I'm sorry. I'm sure I just missed why you only had two cases. There are just two cases in this
Yes, it's sufficient to use two cases because let me say it this way, which is not exactly correct, but is philosophically correct, and that is that this relation is essentially linear in lambda. And so if you do it for short lambdas, it's enough to determine it everywhere. Okay? So that's not exactly correct, but it is the heart of the matter, is that somehow it's enough to do it for short lambdas and to get them for all lambdas. All right. To get what you need for all lambdas. All right. But it is a big group. I mean, there are ways to get t's and then y's and t's and y's, and there are very long words that can't be reduced. So. All right. So the double affine Hecke algebra is probably closer to the double loop group than the double Bray group, but we need to build it. So the first thing we need to do is we need to fix parameters, which I'm going to call ti to the half. All right. Now, there's a subtlety here because this is correct for most double affine Hecke algebras, but it's not correct for type Cn check Cn, which is a very special case. And so I've become confused, and I think that this definition needs to be, like I said, this is not wrong, but it's somehow philosophically not quite the right thing to do, to fix these parameters. But I need parameters. And then the double affine Hecke algebra, is the quotient, so let's call it H tilde, is the quotient of the double affine Bray group by the relations ti check squared is ti to the half minus ti to the minus a half ti check plus 1. All right, so
One more question. You've again and again had a distinguished index 0.
yes.
What does that mean?
So
Or, I mean, do we care?
no, I don't think we care. But the convention is that that's the wall of the chamber that does not go through the origin. But I'm not quite
Which
sure.
of the walls of the chamber that don't go through the origin? I mean, there could be as many as you want.
No, there will only be one. The chamber, the chamber has all of its walls going through the origin except for one.
That's of course not true.
What do you mean?
I mean, in A1 cross A1.
Oh, yes, well, right. No, you better assume it's irreducible, or there are many things that I have to be more careful of. No, you're certainly right. Let's do it. Yeah, let's assume that the underlying W0 is acting irreducibly. Yeah. But you put your finger on a very good point, and that part of the thing that's bothering me with these parameters and so on is exactly the issue that you're talking about. Is that it's not, somehow there are times where I need to say, oh, well, yes, irreducible, and I shouldn't have to do that. And I don't know how to write the theory properly so that I don't have to do that. Yeah. Okay, so that's the double affine Hecke algebra. Now, the double affine Hecke algebra is somehow just right. And you can tell that it's just right because after you work a little bit with these relations, you find that there's a way to make it look like the double affine algebra. So I need to tell you how to do that. So let's let x to the mu equal to SI1 check up to SIL check be a minimal length walk to x to the mu. So this is in the picture of W check. So let's okay. So if I were writing this, this is x to the epsilon 1. Oof. This is x to the epsilon 1 S1 check. This is x to the epsilon 1 S2 check. This is x to the epsilon 2. Remember, I'm identifying W check with these alcoves. So it makes sense for me to point to an alcove and say that's x to the epsilon 2. And this is x to the epsilon 2 S1. And this is x to the epsilon 2 S2. I guess it should be checks there. Okay. So now I'm saying, well, okay, let's take x to the epsilon 1 here, for example. And let's start at the chamber, at the fundamental alcove. And let's walk to that chamber in a minimal length way. All right, so I'm going to fix a minimal length walk to that chamber. In this case, that goes through S0 check, because S0 check is the reflection in the 0 hyperplane. This is S0 check S1, 2, 1, and so on. So that walk is a very precise path from the fundamental alcove to mu. Now, I'm going to create an element in the affine Bray group, in fact. All right, so I need to tell you the periodic orientation. Has 1 on the positive side of H alphas, and it has H alpha check and H alpha check plus some shift have parallel orientation. Okay, so what that means, I really need another pen here. Yeah. What that means is, let's take those hyperplanes that go through the origin and we orient them so that the chamber is on the positive side. So this is oriented minus plus, so that my fundamental chamber is on the positive side of those guys. All right? That's part 1 there. 1, the fundamental chamber is on the positive side of the hyperplanes that go through the origin. So, all right? And then if I have parallel hyperplanes, I make the orientations on parallel hyperplanes parallel. So every one of these hyperplanes now has an orientation, minus, plus, minus, plus. Okay, now we define the following thing. So define x to the mu in the affine Bray group by x to the mu is ti1 check to the epsilon 1 check up to til check epsilon L check, where I make these epsilons are signs. These epsilons are signs, so epsilon k check is minus 1 or plus 1 if the kth step is a positive crossing, and it's plus 1 if the kth step is a negative crossing. Okay, so let's look at this example here. In this x to the epsilon 1, the first step.
Quick question before you do that.
Yeah.
Did you get the labels on the 0th The horizontal lines, correct? Seems like there's a minus going into the chamber on the horizontal lines.
This plus,
No, the other one, down to the right.
this plus,
Yeah.
this plus should be on the same side of this blue line as the chamber
Are you
one.
label the line going through the origin, or you label the line that's actually
The line going through the origin. These guys go through the origin.
all of them? Oh, each alpha, not the numbered ones.
That's right.
Okay.
That's right. These are not the shifted ones, right? Yeah. Okay. All right. So now this first crossing is from minus to plus. This next crossing is from minus to plus because that has this orientation. That's parallel to this one. Minus to plus. The next crossing is minus to plus. The next crossing is minus to plus. So in this example, let me write it here. X to the epsilon 1 is T0 check inverse, T1 check inverse, T2 check inverse, T1 check inverse. And the other one, let's make a path to that one. So for this one, we could do this path, this. And this is plus to minus. So the first step in that one is T1 check to the plus 1. The next step is T0 check to the minus 1. Then T1 check to the minus 1 and T2 check to the minus 1. All right, so I can produce elements. Now here's the amazing statement. These x to the mu's are an abelian subgroup, a commutative subgroup. Of the affine break group.
You've only defined them from mu in the root lattice so far?
Yes, if I need to go out of the root lattice, then I need to put a G check here and a G check here. Yes. The omega can always be moved to the front, and I can put that to. Yeah. Okay.
You've only defined them for distinguished, only one for every octahedron in some sense.
I've only defined one for every octahedron. I could use this definition for every alcove, but the ones that I need right now are the ones for every octahedron. You can make this for every alcove, and actually they are geometrically important. Okay, so now we can say something. H tilde has basis Q to the K on E, X to the mu, T W, Y to the lambda check, K Z, mu in H Z star, W in W0, lambda check in H and in H Z. Oh, I haven't told you what TW is. Where I can define TW where TW is TJ1 up to TJL if W SJ1 up to SJL is a minimal length walk. Okay, so the point is that this affine Hecke algebra, this double affine Hecke algebra, it looks exactly the same as the double affine Weil group. At the beginning, the double affine Weil group didn't look so horrible. But this double affine Hecke algebra is somehow not so horrible, except that I've added some parameters. T check here G checked is not square root of 1 anymore, but it uses this Hecke relation. So it took me some work to build this double affine Hecke algebra. But once I'm done, it's just sort of a Q version, a parameter version of the double affine Weyl group. All right, so, and this is the object which controls all of Macdonald polynomials and so on. So I'll stop there for now.
Okay, and thanks, Aaron. Are there any quick questions?
Just a quick one. I couldn't actually see. Is there a tiny little q there in the bottom in the definition of x to mu?
A tiny little?
A q on the left?
No, this is a G check.
Oh, that's a g check. Okay.
And this was to answer David's question. I was being lazy and not, and only taking things in the
Okay.
grid lattice.
Okay. Gotcha.
And so if I need to correct for that, I need elements of omega.
Okay, if there are no further questions, then I guess we're probably going to need 2 or 3 minutes to get ready for the next lecture, so we'll start again in 2 or 3 minutes. Maybe at 5 past, if you definitely. And you can thank Aaron again.